China built a better moon rocket than NASA, and it cost almost 10 times less. NASA's Space Launch System costs over $4 billion for a single launch, more than the entire budget of some countries' space programs. That's like spending over $75 million every minute the rocket is in flight. You heard that right. And yet, halfway across the world, China is building a rocket designed for the same mission, faster, cheaper, and with a system that's starting to make Western engineers uneasy. Because this isn't about one rocket beating another. It's about how one system became so expensive, it struggles to move, while another is quietly learning how to scale. And the moment you put these two side by side, something starts to feel off. The most powerful rocket ever built shouldn't be this inefficient. So what went wrong? And more importantly, what did China figure out that NASA didn't? The illusion of power. You're told these two rockets are chasing the same goal. Both are built to take humans back to the moon. Both represent the peak of national engineering. Both carry decades of ambition on their shoulders. On the surface, it feels like a fair fight. Then you look at the numbers. NASA's Space Launch System can push close to 200,000 pounds toward the moon in its early configuration, with future upgrades promising even more. It's massive, loud, built like a machine that forces its way into space. China's Long March 10 comes in lighter, lower payload, less raw thrust on paper. At first glance, it looks like the weaker system. And that's where the comparison starts to mislead you. Because the moment you assume bigger means better, you miss what's actually happening. The Space Launch System is designed around a single idea. Lift everything in one go. One rocket, one mission, one massive push. It's a direct continuation of the Apollo mindset: brute force your way to the moon with the most powerful vehicle you can build. And for a long time, that approach made sense. But this was just the beginning of the problem. China didn't follow that path. Instead of relying on one giant rocket, Long March 10 is part of a larger system, multiple launches, separate components, pieces that meet in orbit and assemble before heading to the moon. At first, that sounds more complicated. More moving parts, more chances for something to go wrong. But then, you start to see the shift. Because complexity on paper doesn't always mean complexity in practice. A modular system spreads risk. It allows smaller, more frequent launches. It creates flexibility. If one part fails, the entire mission doesn't collapse under a single point of failure. Meanwhile, SLS carries everything on its back. And that creates a different kind of pressure. Every launch has to be perfect. Every component has to work, because there is no second chance built into the system. And suddenly, the rocket that looks more powerful starts to feel more fragile. But the deeper issue isn't risk. It's sustainability. Because once you step back, you realize something uncomfortable. A system built around a single massive rocket is incredibly hard to scale. You can't launch often. You can't adjust easily. You can't experiment without risking billions. So even though SLS dominates in raw strength, it moves slowly, carefully, expensively. And then you look at China's approach again. Multiple launches mean higher cadence, more opportunities to refine, faster iteration, a system that improves as it operates. And it wasn't just about engineering. It was about philosophy. One side built a rocket to win a mission. The other built a system to repeat it. But the silence didn't last. Because once you start comparing them this way, the numbers stop being impressive. They start raising questions. If the most powerful rocket ever built can only fly occasionally, is it really the more capable system? And if a smaller rocket can launch more often, adapt faster, and build momentum over time, does raw power even matter anymore? That's when the comparison shifts. You're no longer asking which rocket is stronger. You're asking which system is built to last. And that question leads straight into the part no one expected to matter this much: the cost. The cost changes everything. You start with a number that sounds unreal. Over $4 billion. That's what it cost to launch NASA's Space Launch System once. One rocket, one mission, one moment of liftoff. To put that into perspective, that's more than what it takes to build multiple modern fighter jets or fund entire national infrastructure projects. It's like burning through over $60,000 every second from ignition to orbit. You heard that right. And at first, you assume there has to be a reason. This is NASA, the most experienced space agency in the world. The rocket is powerful, complex, human-rated. Of course it's expensive. But this was just the beginning of the problem. Because when you start breaking that number down, the logic begins to fall apart. The engines on SLS aren't even new. They're upgraded versions of the same RS-25 engines used on the space shuttle decades ago. The solid boosters? Also derived from shuttle-era designs. Even parts of the core structure trace back to older systems. This isn't a brand new rocket built from scratch. It's a machine assembled from legacy components with a price tag that somehow kept rising anyway. And then you realize something more unsettling. The system behind SLS was never designed to reduce cost. It was designed to sustain it. Multiple contractors across different states. Massive supply chains spread out intentionally. Each piece built by a different company. Each contract structured in a way that rewards time and complexity instead of efficiency. This is what's known as cost plus contracting. The longer it takes, the more it costs, the more money flows through the system. And it wasn't just engineering that shaped the rocket. It was politics. Jobs needed to be protected. Contracts needed to be distributed. Facilities that existed from the shuttle era had to be kept alive. So instead of asking, what's the fastest and cheapest way to build this? The system asked, how do we keep everything running? And that changes everything. Because now the rocket isn't optimized for performance alone. It's optimized to satisfy a network. And that's when the number stops feeling like a necessity. It starts feeling like a symptom. But the silence didn't last. Because halfway across the world, a completely different approach was taking shape. China's Long March 10 doesn't come with a public price tag as detailed as NASA's, but estimates place it far lower, in the range of a few $100 million per launch. Even if you adjust for uncertainty, even if you double or triple that number, it's still nowhere close. And that gap forces a different question. How can two rockets built for similar missions end up in completely different cost universes? The answer isn't one breakthrough. It's structure. China's system is vertically integrated. Fewer contractors, more centralized control. Decisions move faster. Designs change without layers of negotiation. There's no need to distribute work across regions for political reasons. There's no incentive to stretch timelines. And that creates something NASA lost over time: pressure to be efficient. Lower labor costs play a role. Centralized authority plays a role. But the real difference is how the system responds to time and money. One system slows down and absorbs cost. The other compresses both. And then comes the part that changes how you see everything. Because cost doesn't just affect budgets. It affects behavior. When each launch costs billions, you hesitate, you delay, you test endlessly, you minimize risk at all costs. But when launches are cheaper, you move, you launch more often, you learn faster, you iterate in real time, and suddenly, the advantage shifts. Because space isn't won by one perfect mission, it's won by repetition. And it wasn't just the rocket that was affected. It was the entire pace of progress. NASA built a system where every launch carries enormous weight. China is building a system where launches become routine. And that difference is hard to ignore. Because one of these models leads to presence. The other leads to pauses. And this is where the tension peaks. If one country can launch more frequently, adapt faster, and spend less doing it, how long before that advantage compounds? How long before cost stops being a limitation and starts becoming a weapon? Then came the realization that ties it all together. You're not comparing engineering decisions anymore. You're comparing incentives. One system rewards continuation. The other rewards acceleration. And once you see that, the next question becomes unavoidable. How did one system end up moving so much faster than the other? Speed becomes power. You expect the most advanced space program in the world to move fast. After all, this is the same agency that once put humans on the moon in less than a decade. So when you look at the timeline for the Space Launch System, something feels off. The program was officially announced in the early 2010s. It was meant to carry forward the legacy of Apollo and replace the Space Shuttle, a powerful, reliable rocket to lead the next era of human spaceflight. That was the promise. But the years kept adding up. Design revisions, budget negotiations, contractor delays, testing cycles that stretched longer than expected. Each step made sense on its own. Safety checks, engineering validation, oversight, all necessary. But together, they created drag. And it wasn't just the timeline that stretched. Momentum slowed down. Every delay forced another adjustment. Every adjustment triggered more reviews. Progress became something that had to be negotiated, not executed. Then came the first launch. Over a decade after the program began, SLS finally flew. A powerful, historic moment, but also a revealing one. Because in that same window of time, something else had been happening. China had been building. Quietly, consistently, without the same level of public scrutiny or political debate, their engineers were moving through development cycles at a different pace. And this was just the beginning of the contrast. While NASA worked through layers of coordination, China operated through centralized direction. Decisions didn't need to pass through multiple committees. Designs didn't stall, waiting for cross-agency alignment. They moved. And that speed started to show. Prototype development, testing phases, iteration cycles, each one compressed, not rushed blindly, but executed with fewer interruptions, a system designed to maintain forward motion. But the difference wasn't only structural, it was cultural. NASA operates under intense visibility. Every failure is public, every mistake analyzed globally. That creates caution, a deep, necessary caution shaped by past tragedies. And it wasn't just caution. It was responsibility. Human lives are involved. National reputation is involved. The margin for error is almost non-existent, so the system slows down. Not because it can't move faster, but because it chooses to protect against failure at every level. China operates differently. There is less public pressure, fewer external voices shaping the process. Failures still matter, but they don't carry the same global scrutiny. And that changes how risk is handled. It allows faster iteration, faster correction, a willingness to move forward without waiting for perfect certainty. And suddenly, speed becomes more than a timeline. It becomes an advantage. Because in space, the program that moves faster gathers more data, tests more systems, learns from more launches, builds experience in real time. And experience compounds. Each mission informs the next. Each iteration refines the system. Progress accelerates, not in a straight line, but exponentially. But this was just the beginning of the imbalance. Because when one system moves slowly, it doesn't just fall behind. It creates gaps. Gaps in knowledge, gaps in readiness, gaps in presence. And those gaps can be filled. China's faster pace isn't only about reaching the moon sooner. It's about building capability continuously, establishing reliability, creating a rhythm of operations that becomes harder to match over time. Meanwhile, NASA's system moves in intervals. Long gaps between launches, long preparation cycles, long decision loops, and that creates a different kind of risk. Not failure, irrelevance. Because while one system is preparing, the other is operating. And it wasn't just about rockets anymore. It was about momentum. The kind of momentum that builds quietly until it becomes impossible to ignore. And then comes the realization that shifts everything again. If one country can design, test, and launch faster, while the other remains locked in extended cycles, Who controls the timeline of the future? Because in space, timing isn't secondary. It's strategic. And the system that moves first often sets the rules for everyone else. But the deeper question still remains. What allowed one system to move this way in the first place, while the other became so constrained? Built by two systems. You start looking at the rockets again, but this time, you're not focused on what they do. You're focused on how they were built. Because that's where the real difference begins to show. NASA's Space Launch System wasn't created from a blank slate. It was built on top of something that already existed. Engines carried over from the space shuttle, boosters adapted from older designs, infrastructure that had been in place for decades. At first, that sounds efficient. Why reinvent what already works? But this was just the beginning of a deeper issue. Because those decisions weren't driven purely by engineering. They were shaped by preservation. Facilities that needed to stay open, contractors that needed to stay funded, supply chains that had been in place for years, now too large to simply shut down. So, instead of designing the most efficient rocket possible, the system designed a rocket around what already existed. And that changes how everything fits together. Each component comes from a different place, built by different teams, managed under separate contracts, coordinated across layers of communication that stretch the process further than expected. And suddenly, the rocket isn't a single machine anymore. It's a collection. A structure held together by agreements as much as engineering. And it wasn't just complexity that came with that. It was dependence. Each piece relies on another. Each delay ripples through the system. Each adjustment requires alignment across multiple groups before anything can move forward. And that creates friction. The kind you don't see in the final launch, but feel in every step leading up to it. But the silence didn't last. Because when you shift your attention to China's Long March 10, the structure feels different immediately. This wasn't built to preserve the past. It was built to serve a goal. Fewer contractors, more centralized development, systems designed together, not stitched together later. That difference seems subtle at first, until you see how it plays out. Decisions move faster because fewer parties are involved. Design changes happen without negotiation across dozens of stakeholders. Components are built with compatibility in mind from the beginning. And that creates something NASA's system struggles with: continuity. Because when one team controls more of the process, the rocket behaves like a unified system. Fewer surprises, fewer integration problems, fewer points where something can go wrong simply because two parts were never meant to align perfectly. And then comes the part that shifts the perspective again. Because this isn't about which engineers are better. Both sides have world-class expertise. Both are capable of extraordinary precision. The difference is what the system allows them to do. NASA's engineers operate inside a framework shaped by decades of legacy. Every decision connects to something that came before. Every change has consequences beyond the immediate design. China's engineers operate inside a framework built for output. Fewer historical constraints, fewer dependencies, more room to align the entire system around a single objective. And that creates two very different outcomes. One system evolves slowly, protecting what exists. The other builds forward, focused on what comes next. But this was just the beginning of the divide. Because once you step back, you realize the rocket itself is only one piece of a much larger structure. The way it's built determines how it can be used. SLS is powerful, but difficult to adapt. Each launch requires coordination across a wide network. Each mission becomes a major event. Long March 10 is part of something more flexible. A system that can adjust, scale, and repeat without carrying the same structural weight. And that difference isn't visible in a single launch. It shows over time, in how often missions can happen, in how quickly improvements are made, in how easily the system can respond to new goals. And then, the realization lands. One rocket was built to work. The other was built to keep working. And that distinction changes how you see everything that comes next. Because this isn't only about reaching the moon. It's about what happens after you get there. and whether your system can keep up once the race stops being about arrival and starts being about presence. But this is where the story shifts one final time. Because the most important question isn't which system is better built. It's what that difference means for the future of power in space. This isn't about the moon. You start to realize something uncomfortable. This was never really about the moon. That's the headline. That's the destination. That's the part that feels familiar. Humans returning to the lunar surface, planting flags, building missions that echo the past. But beneath that, something else is taking shape. Because rockets don't win space. Systems do. And the moment you step back from the hardware, the comparison changes completely. The Space Launch System is designed to get you there. It's powerful, precise, capable of carrying everything in one massive push. When it launches, it delivers. But delivering once isn't the same as staying. And that's where the tension begins to build. Because every single SLS launch carries enormous weight, billions of dollars, years of preparation, a level of coordination that turns each mission into an event that can't easily be repeated. And that creates a limitation no one talks about enough. You can't build a constant presence on something that only moves occasionally. But this was just the beginning of the imbalance. Because while one system prepares for rare, high-stakes missions, the other is quietly building frequency. China's approach isn't centered on one defining launch. It's built around repetition. Multiple missions, modular assembly. A system designed to operate again and again without collapsing under its own cost or complexity. And that changes the objective. Because once you can launch more often, everything accelerates. You can move equipment in stages. You can correct mistakes without resetting the entire mission. You can build infrastructure piece by piece instead of risking everything on a single attempt. And suddenly, space starts to look less like a destination and more like a network. But the silence didn't last. Because once that network begins to form, the advantage compounds. More launches mean more data. More data means faster improvements. Faster improvements mean a system that evolves while it operates. And that's when the gap starts to widen. Because one side is executing missions. The other is building momentum. And it wasn't just about rockets anymore. It was about presence. The ability to show up again and again, to establish reliability, to create a rhythm of operations that turns space from something occasional into something continuous. And that's how control begins. Not through one breakthrough, but through consistency. NASA still leads in many areas: deep space science, precision engineering, international collaboration. There is no question about capability. But capability alone doesn't decide the outcome. Structure does, and the structure behind SLS makes repetition difficult. Every launch is expensive. Every mission is heavy. Every step requires time that can't easily be compressed. And while that system protects against failure, it also slows down progress. China's system carries its own risks: centralized control, different transparency standards, a model that doesn't operate under the same public accountability. But that system moves. And in a domain where speed compounds into advantage, movement matters. Because space is shifting. It's no longer about who can reach orbit. It's about who can operate there continuously. Lunar bases, resource extraction, permanent infrastructure, systems that don't just visit but stay. And that requires something SLS struggles to provide: cadence, the ability to launch again and again and again without resetting the entire process every time. And that's when the realization hits hardest. If one system can build presence faster, cheaper, and more consistently, it starts defining the environment itself. Routes, standards, timelines, not through dominance, but through repetition. And once those patterns are set, they're difficult to reverse. But this was just the beginning of what makes this shift so unsettling. Because the same principles don't stop at the moon. They extend further, to Mars, to deep space logistics, to satellite networks, to the infrastructure that will shape how space is used for decades. And the system that learns to operate efficiently now carries that advantage forward. Meanwhile, the system that struggles with cost and speed has to catch up while the game is already in motion. And it wasn't just NASA facing this pressure, because when one model proves it can move faster and cheaper, it forces everyone else to respond. The entire balance starts to shift, and that's what makes this comparison so much bigger than two rockets, because what you're really looking at is a transition. From one way of building power to another, one built on scale, legacy, and caution. The other built on efficiency, integration, and speed. And neither is perfect, but only one is accelerating. And that leads to the question that sits underneath everything. If the future of space belongs to the system that can operate continuously, what happens to the one that can't? Because at some point, power stops being about who can reach the moon and starts being about who never has to leave. And that's when the title stops feeling like a comparison. It starts feeling like a warning. China didn't build a better rocket by accident. It built a system that made a better outcome possible. And once you see that, you can't unsee what comes next.